Hi, hello. I'm Bear, and today we're going to take two on the chin by doing something I really don't enjoy doing. A code walkthrough. Except, instead of this being like a melatonin pill became sentient and punched you in the mouth, I'm going to try to keep this interesting. Also, #ad, this video is sponsored by my last video. I'd recommend it. Not only because it cured my incontinence, but also because it helped me save a bunch of money by automatically selecting coupon codes and helps me trim my balls. With that out of the way, let's learn about genetic algorithms by solving the knapsack problem. We are going to do this a bit different than what you're probably used to, as most code walkthroughs are dry, time-consuming, and focus too much on the code over explanation. And also because I much rather gouge my eye out with a spoon from Steven Tyler's silverware drawer than work on a boring video for weeks. With this being said, in the description you will find a link to my GitHub where I have posted the code in its entirety. Use this link, copy my code, and then watch the rest of the video. Also, as an aside, I'm using both C# and Visual Studio for this project, and if you don't know what a genetic algorithm or the knapsack problem is, go watch my last video because, boy, are you going to be confused. Alright, as long as you aren't the rebellious type and copied my code, you should be ready to run the application. Press F5 and the console should pop up and start doing stuff. I know I haven't really explained anything yet, but just humor me. The initial settings I chose should be easy for just about any computer to accomplish, and it should have flown by in just a matter of seconds. The real meat of the application and why we are here is the final stats. As you can see, this is split into two different categories: contextual and performance information. All the contextual stuff is self-explanatory if you watch my last video. The performance information is why we are here. As you can see, it's fairly basic, but it gives us all the information we need to see how well the algorithm is working. The first 3 lines of the performance information is the algorithm's history. The last 3 lines are what's important. As you can see, the algorithm works with pretty good accuracy and fairly quickly. Quite a big difference from the 12 trillion years I said in the last video. Filling the backpack up to 99.999% of its total fill volume in 2 seconds is a win in my book. Kinda cool, right? Well, maybe not without context of what the algorithm is actually doing. So, let's do that. As I discussed in the last video, genetic algorithms use bots as the main form of information transfer and does the work for us. To create a bot, I needed to make a separate class so I can have an entire population of bots. This class has 3 class members and 1 constructor. The list chromosome is its decision tree for which items to use. The fitness value and chromosome weight variables are used in the selection phase and will be explained later. And the constructor is used to automatically initialize the chromosome as a new list. And literally, this class is just set it and forget it. Once we have it coded in, we can forget about it like it was the middle child of a wealthy family. With that out of the way, let's look at the groundwork for the knapsack problem. We need a few things to create the problem we are trying to solve. We need a backpack, items to put in the backpack, and a random number generator. For the genetic algorithm side, we need to keep track and sort through all the bots. We do this with a list that we call the population. With these 4 variables in mind, we can initialize them using a separate function and calling it in the main function. Everything is cut and dry here except for the bag weight. We could just pick any random number and keep it the same every time we run the application, but instead, to make sure the algorithm is actually doing its thing, we set the bag weight to a random number in a range that we can decide on. With initializing done, we can move on to creating the actual items we are going to use. We do this in a separate function called createItems, and it's really simple. All we do is use a for loop to add a bunch of random numbers to a list. After all, the only important information here is how much each item weighs. Each random number represents an item. How many items and how much each item weighs, we can determine later using a few well-placed variables. Alright, with that out of the way, let's talk about genetic algorithms. You may remember this chart from my last video. If so, You know the first step is to initialize the first, ultra-dumb population. Except instead of being like Pokemon, this first gen is destined to be forgotten and not all that cool. In a separate function, we are basically only doing 3 things. We are initializing the bot using the bot class we created, adding decisions to its chromosome, and then adding the bot to the population list. Initializing the bots and adding it to the population are self-explanatory. The only thing to keep in mind is that we are using another well-placed variable here to be able to control the population size later. What is important to go over is the nested for loop that is responsible for assigning decisions to the chromosome. The chromosome needs to have a length as long as the number of items to choose from. Hence, we are using the same variable that controls how many items there are. After all, this is the stage in which we randomly tell the stupid bots from the first generation whether to include or exclude an item. To give each bot its decisions, we are adding Boolean values to its chromosome until the list is full. To decide on which bool to give the bot for each index, we use the getBool function, and its only purpose is to flip a coin. Heads, or in this case, 0, we return a true value. Tails, or 1, we return a false value. The return value is added to the list, essentially giving the bot its decision for that item. Another great way to think about this is that the items list and the chromosome work in tandem. If index 22 of the items list is an item that weighs 8 pounds or something, then index 22 of the chromosome is the bot's decision to that item. True would mean include, false would mean exclude. If we do this for every bot in the population, this would mean that each bot has a completely different chromosome, making each bot's decision unique, though incredibly dumb. We could prove how dumb the first population is by running the application and looking at the final stats again. The first line under the performance information tells us how the top performer in the first generation did, and as you can tell, it missed the mark by a few 100%. Mathematically speaking, this makes total sense when you think about a coin flip. The chances of getting a heads is 50-50, meaning the entirety of the first generation is going to include roughly about 50% of all the items, give or take, which causes the first generation to miss by a lot. The next few steps are going to repeat with every generation. The first step is the selection phase now that we have the first generation. As I said in the last video, we are using truncation selection as it's the easiest to understand and it works just fine for what we are doing. We're testing the bots to see how close they got to the bag's weight limit using their chromosome, giving them a score based on the test. Sort them, then select the bots to breed, right? Well, there is a problem, and this is why I said this is not the best way to do this. If we go off the conventional method of if they're under the bag's weight limit, they get a score based off of how close they were, and if they're over, they get a 0, if we remember how dumb the first population is, we can tell the entire first population is going to have a fitness score of 0. Does this mean they all equally perform terribly? No. This means that we need a secondary metric, which is also why the bot class has 2 variables to use during the selection phase. The most important metric is the fitness value because that's its true positive performance score. But in the situation where there is no positive performance score, we still need to organize the bots based off how close they got. This can be seen in this section of code. Basically, we loop through each bot in the population, compare its chromosome with the items list. If the bot chose to include the item, we add its weight to a total, effectively giving the total weight of the chromosome. We then have that bot save that weight as the secondary fitness score. Then compare that weight against the bag's weight limit and assign its fitness score. Once we have its 2 fitness scores, we can sort the bots based on those 2 scores. First, we attempt to sort the bots based on the fitness value in order of descending because the higher the fitness value, the better the bot performed. We then check the fitness value of the first bot in this sorted list. If the first bot has a fitness score of 0, we know all the bots have a fitness score of 0. In this situation, we can then sort the bots in order of ascending based on their chromosome weight, because if they're all over the bag's weight limit, the lower the chromosome weight, the closer they are to the bag's weight limit. No matter how you had to sort, we add our sorted bots to a new list so we can clear the population for the new generation. With the bots sorted, we can now select the top 50% of the bots and feed them into the crossover and mutation phase. As I said before, the first step of crossover is Star Wars Episode 2: Attack of the Clones. We use clones to make sure the generation has to compete to be better than the last generation. If they aren't, then having the clones in the mix is basically like giving the algorithm a chance to reroll. Without clones, if the next generation happens to perform worse, we are stuck with the bad roll and we have to hope that the algorithm will come back around. This stage is as easy as taking the first 10% of the sorted population and adding them to the new generation. This stage is called cloning, but programmatically it's like taking the top 10% and letting them stay in the workforce while the other 90% are forced to retire. To replace the remaining 90%, we breed a new generation. And considering we are only using the top 50% of the old bots to replace 90% of the new generation means, true to the real world, each pair needs to have 2 children to maintain the population. And this can be seen in this section of code. If there are kids in the room, tell them to cover their ears, because it's time to talk about breeding. As I said, crossover is as simple as picking a random number and combining the list of both parents at that point, making one half of the new list from one parent and one half from the other. But also, at the same time, we are checking for a mutation. To do this, with every gene copied, we roll a random number between a minimum and a max of our choosing, and if the random number ever hits 1, we mutate the gene by flipping the value true to false or vice versa. The process of crossover can be seen here, but there is one small difference between the copy I left in the description and what I have on screen now, and that's the position of this line here. To get a chromosome output as I described above, with a clean split, one half being from one parent and the other half being from the other, you need to select the crossover point before you start looping. But there are always better ways to do things. I did some testing and found that if you randomly roll the crossover point with every iteration, you get better results. If you don't believe me, here's some stats. And I figured this simple change in positioning gives your new chromosome a blending type effect between the two parents' chromosomes, where instead of it being a clean split, there is a fade in/fade out type effect between the two. The process of crossover replenishes the remaining generation, and upon finishing, we can tell by the main function that the whole process loops back to the testing phase. This process will repeat for as many generations as we have assigned. If you want to play with the settings and try harder combinations and see what the algorithm can do, there are a few settings variables that you can tinker with. All are self-explanatory, and I have left a few unnecessary comments to describe what each does. There are 100 different ways that you can write this algorithm, which makes it kind of hard to explain. So the best thing you can do is play with the algorithm, use this video and my code to see if you can rewrite this algorithm from scratch. And try to understand the concepts and ideas instead of copying someone's code verbatim. Because going from here, every genetic algorithm for every problem you are trying to solve will be different from the last one. Meaning no amount of tutorials and code will help you if you don't understand what's happening and why it works. And that's it. Thank you for watching. In the next video, we are finally going to actually play around with genetic algorithms and have the AI play Flappy Bird or the Dinosaur Run game or something. I'll figure it out. Like, comment, and subscribe down below. If you don't, then I'm gonna tell my mom. Okay, bye.